Surface tension is a property of liquids that results from the tendency of liquids to minimize their surface area. So to minimize their surface area, liquids will form drops that are spherical only in the absence of gravity, though. If there's gravity, that's going to pull it down. It's going to change the shape. And they form spheres because spheres have the lowest surface area. In a liquid, the layers of molecules on the surface behave different than the ones on the interior. The ones on the interior are getting pulled in all directions by the other particles around them, but the ones on the surface don't have any on the top kind of pulling them up. And so they're getting pulled just by the ones next to them and the ones below them. And so what that does is it kind of stretches the surface tight like a drum, or like stretching like plastic wrap over a bowl. And the surface area then will act like kind of an elastic skin. So this spider can float, or he's not floating, he's actually standing on top of the water. You can see there's the little dimples there. So his little legs are kind of making a little dimple in the surface layer, but they're not breaking through. Surface tension is affected by intermolecular forces. The stronger the intermolecular forces, the higher the surface tension will be, the more tightly those particles will be held. So if we were comparing water and acetone, water, as we know, looks like that. Acetone is like this. So water, as we know, hydrogen bonds, big dipole moment. Acetone just has that one little polar part in the middle there. And so acetone would have weaker forces. Acetone would have a lower surface tension. Temperature also affects surface tension. Raising the temperature reduces surface tension. Anytime you raise the temperature of a liquid, the particles are going to start moving more. If the particles are moving more, those intermolecular attractions are not able to hold on as strongly. One of these compounds is liquid at room temperature. Which one and why? So formaldehyde, we have this dipole right there. For fluoromethane, we have one right there. And then methanol, we know we have one right there. So both formaldehyde and formaldehyde and fluoromethane have dipole-dipole forces working because they are polar molecules. But methanol, because it's an OH, yes, it's a dipole-dipole force because it's a polar molecule, but we have a hydrogen bonded to oxygen, which is one of those three special, nitrogen, oxygen, fluorine, that would make it a hydrogen bond. So because methanol hydrogen bonds, that has the strongest forces, so that would be most likely to be liquid at room temperature. Viscosity is the resistance of a liquid to flow. So things that are going to affect viscosity are, of course, going to be intermolecular forces. Stronger intermolecular forces are going to hold molecules more tightly. It's going to be harder for those molecules to slip past one another. So that's going to give you a higher viscosity. Bigger particle size gives you a higher viscosity. This is why things that contain sugar, like syrup or honey, are thicker and harder to pour. They have a higher viscosity than something that has a smaller particle like water. And then a higher temperature is going to give you a lower viscosity for a similar reason to what I was just talking about with surface tension. If there's a higher temperature, the particles are moving around more, the intermolecular forces are not able to grab hold as strongly, and so it will be easier for those particles to flow past one another. So if we were ordering these from lowest to highest viscosity, of course, the first thing we would have to do is determine the forces in each. So acetone, we just talked about, has that little dipole moment there, so it is dipole-dipole. Hexane and butane are both nonpolar, so they're both just dispersion forces. Propyl alcohol, we have a dipole moment right there, so it's dipole-dipole, but it is oxygen bonded to hydrogen. So when you have a dipole-dipole, the next thing you need to check is, okay, do I have a hydrogen bond? And this one does. So that's more important, that's stronger. Water, as we know, hydrogen bonds. And ammonia, of course, remember, is trigonal pyramidal. That's its shape, so it is polar. So dipole-dipole. Check if it hydrogen bonds. Oh, yeah, hydrogen bonded to nitrogen. So that's a hydrogen bond. So lowest to highest viscosity, if I translate that in terms of forces, lowest viscosity is going to be the weakest, and then highest viscosity is going to be the strongest. So I'm going to order these from weakest forces to strongest forces. Both butane and hexane have dispersion forces only acting in them. When comparing dispersion forces, you need to then go to particle size. Butane is smaller, so it has weaker forces. So butane is going to have the lowest viscosity, and then hexane. And then we go to our next strongest force, the dipole-dipole, so that's the acetone. And then we have our 3 hydrogen bonds that we need to compare. Of those 3, the propyl alcohol will be the weakest because it just has that one little polar area as opposed to the entire molecule being polar. And then after propyl alcohol is going to come ammonia, the NH3. And that is because the NH bond is less polar than the OH bond. So even though there's more H's, that doesn't really have anything to do with it. It's at this point when we're comparing hydrogen bond to hydrogen bond, it's about which bond is more polar. And so again, the OH bond is more polar than the NH bond, so the NH bond is a little bit weaker. And then my strongest force would be in the water, so that would be the highest viscosity. Capillary action is the ability of a liquid to flow up a thin tube against gravity. So even though there's gravity present, the liquid can still travel up the tube. The narrower the tube, the higher the liquid is going to rise. Capillary action happens because of both cohesion and adhesion. Pretty much everything we've been talking about to this point is just cohesion. 2 of the same particles being attracted to each other, like water molecule to water molecule. But capillary action brings in adhesion as well. So cohesion, again, is holding the liquid molecules together like water to water. Adhesion is between 2 different particles, so water to glass in the side of a tube or something like that. So what happens is the adhesive forces, the water, if it's water, sticks to the glass. Okay, that's an adhesive force. And so the adhesive forces pull the surface liquid up the side of the tube. And then the cohesive forces, water molecule to water molecule, pull up other molecules behind it. So like one water molecule sticks to the glass because of adhesion and then pulls up other water molecules with it because of cohesion. The liquid will rise up the tube until the force of gravity, kind of counteracts it and it can't fight gravity any longer. And the narrower the tube, the higher the liquid can go. If we look at these tubes here, there's water right there. And the tubes are open at the bottom and they're placed into the water, and the water just, because of capillary action, travels up the tube. So in this widest tube, it's right there, right there, right there. And so you can see in that very thin tube how much higher it rises. And the reason for that is, again, because of the adhesive forces. When the tube is very thin, there are more water molecules or more liquid molecules in contact with the glass. So there's more adhesion going on there. Whereas when the tube is very thick, all of those ones in the middle are not in contact with the glass. And so they are not experiencing any adhesive forces pulling them up the side. Cohesion and adhesion is also what causes a meniscus. A meniscus is the curving of a liquid in a tube. So if you look at these here, I'm drawing their meniscuses, it is not perfectly flat. It kind of makes this little U-shaped bend. And again, this is because of adhesion. The water molecule sticks to the side of the glass, and then cohesion forces will pull other molecules along up next to it.